So first thing, course overview. So the course has roughly 2 halves to it. And the first half of the course is a bit different from the usual style of the MDS program in that our sort of tagline is we're going to teach you responsible use of data science tools. And so in Supervised 1, you learned about these methods and how to interpret the output and overfitting and when it's a good idea and a bad idea and all that kind of stuff. But for the next just 2 weeks, we're going to delve a little bit into how these methods are implemented. We also did a little bit of that in algorithms and data structures. Again, trying to strike that balance and make this program the most useful to you. So when I say numerical methods and optimization, we'll just, for example, go a little bit into, say, how is least squares implemented or logistic regression or stuff like that. Then the second half of the course is going to be about deep learning, which is essentially neural networks. And that'll be more in the usual style of 571 and that kind of thing. OK, so there was a video that you were supposed to watch. However, I realized today is the first day of term, and maybe not all of you got my message, or you got my message, but I accidentally said the class was on Tuesday, so you didn't watch the video. I'm just curious, who watched the video? OK, great. So more than half, maybe 3/4. So the video introduced the idea of optimization, and that's actually something you've seen before. And there might have even been a bit of overlap between the video and stuff we talked about in the algorithms course. And so it was talking about, well, you can maximize a function, minimize a function, and all the things that make it easy or hard to do so. And so in algorithms and data structures, we talked about discrete optimization. So for example, scheduling. We could have a TA on a course, and we could pick this TA or this TA or this TA. We had a sort of fixed set of discrete choices. And then we did the same thing with the seam carving, so you could pick this pixel or that pixel. What we're going to do in this course is still optimization, but it's continuous optimization. So the methods are actually totally different. And what's happening here is that we can just pick any number. And where this is going is those numbers are going to be the parameters of our model. So for example, if you're fitting a line, you pick all those regression coefficients. Those can be any number. They're not just picking from a discrete set of choices. So that's why we call it continuous optimization. OK, so I have some true or false questions here. And for those of you who haven't watched the video, maybe try to chat with someone who has one. All right, so the next 30 minutes or so, we're going to be talking about gradients. And I put review in quotation marks. So for some of you, this will be review. But for many of you, this will be new. It's not a prereq to participate in the MDS program that you've taken this kind of multivariable calculus before. Some of you will have if you studied engineering or whatever. But I'm going to try to talk about it from scratch because it's super important for what we need to do in this entire course. So this is essentially just like the one little piece we need from that type of more advanced calculus course, and we don't really need the rest anyway. So we'll just talk about this. OK, here we go. So I have split up where I'm going here into a bunch of different ingredients. And the first ingredient we need is the idea of a function of multiple variables. And that you all have definitely seen before in all sorts of contexts. So for example, in the probability course, you saw joint distribution. So that was a function of multiple variables, like f of xy. If you had 2 random variables, you put in 2 numbers, and 1 number comes out. That's what it means. So you could write it as f of x, y, z, or you could write it as f of x if x is a vector. And here's an example. So this is just a random function I made up of multiple variables. It takes in 3 inputs, x, y, and z, computes some weird thing, and gives us 1 output. And here is the code version of that. And I can run the code, sorry. And it gives me 1 number. So another example is f of xy equals sine xy. Again, that's a function of 2 variables. And when you have a function of two variables specifically, you can make nice visualizations. When you have more variables, it becomes harder and harder to visualize. So here is a visualization. Okay, so what we're seeing here is we have x on the x-axis, y on the y-axis, and the color is representing f, the function, which is in this case sine xy. And so instead of color, if you prefer, you could think of the function coming out of the page. But I'm assuming you saw pictures like this in the probability course where maybe you had a bivariate Gaussian, and so you had some colorful thing. And again, you had to input the two parameters, and then you had some probability density that was illustrated in color. Any questions about this? Okay, so a coordinate in these axes represents the inputs, x and y, to our function, and the color represents the output, the function value, sine x and y. This is a function mapping from two numbers to one number. Okay, ingredient number 2 is vector-valued functions, meaning functions that have more than one output. What we talked about there, we only had one output, like sine xy. And so maybe you haven't encountered these before, but we really just extend our ideas that we have already. So here's an example, f of x, that is a function with one input, x, just a number, like 5, 7, whatever, and 3 outputs, and I'm writing it like this. So the output, you could either think of it as 3 numbers, or the output is a vector. Those are equally valid ways of thinking about this function. But this function f, you give it one number, it gives you back 3 numbers, or alternatively gives you back a vector with 3 things in it, and this is just an example. Now you could have functions with multiple inputs and multiple outputs. So here, this function f, you give it 3 numbers, it gives you back 4 numbers. And again, I'm just making up some mathematical stuff. There's nothing to read into that, but I'm just giving you an example. And here's another one with 2 inputs and 2 outputs. Any questions about this? Okay. So here is this last one at the bottom here, fxy equals x sine y. So I give it 2 numbers, 2 and 10, and it gives me back 2 numbers, 2 and negative whatever. Okay. So when functions have 2 outputs and 2 inputs, we can also visualize them. But again, once we get to more than 2, it's hard to visualize. So we already visualized earlier a function with 2 inputs and 1 output. Now we're going to try to visualize a function with 2 inputs and 2 outputs. You can ignore this plotting code as usual. But here's how you can visualize this. Again, we need a 2-dimensional plane for our figure for the 2 inputs. That's the same as before. But now we can't just use a color to represent the function value, because the function value is not just a single number anymore. The function value is 2 numbers. It's a vector of length 2. So one way you can draw a vector of length 2 is with a little arrow, just the way you drew vectors from the beginning in your linear algebra course. You know, the vector 2, 1 would be drawn like that, or whatever. So what it means is that around here, I'm assuming the output is something like 0, 0, because I don't see any arrow. And around here, on the middle right, I'm assuming the output is something like a big number and 0, because the horizontal arrow. So maybe, I don't know, 2, 0 or 5, 0 or whatever, that's going to look like a horizontal arrow. And so the length of the arrow tells you the size of the number, and the direction of the arrow kind of tells you something about the relative values of the 2 numbers. So here on the left, I probably have a negative something and then a 0, and here I have neither of them 0 because it's not horizontal nor vertical, etc. So this way of visualizing, first of all, the idea of functions with multiple outputs may be new to you, and second of all, this way of visualizing this kind of function may be new to you. So this would be a good time if there are questions. Yes?
Could you just repeat what the direction of the arrow tells you?
It's any, right? So let's not read in too much into the direction of the arrow, because that's actually not too important to us. But basically, for each arrow has an x component and a y component when we draw it. And the first number coming out of the function is the x component, and the second number coming out of the function is the y component. So if the output of our function is 2, 1, we might draw an arrow like this. And if the output of our function is 2, 5, we might draw an arrow like that, and so on and so forth. Other questions? Okay. So there's some text here just analyzing this picture. It's not that important right now. Yeah, I guess what the important thing right now from all that text in the bottom is that the number of inputs and number of outputs are the same here. They're both 2. And that is allowing us to draw this type of picture because in a sense, the inputs and outputs live in the same universe, this 2-dimensional universe. And that property is going to be coming up a lot this week. Okay, ingredient number 3, partial derivatives. So again, many of you may have seen partial derivatives. Many of you may have never heard of partial derivatives, but I'm assuming you have all heard of regular derivatives. So a partial derivative is just a derivative, except the regular derivative in the first calculus course, the function you're dealing with goes from one variable to one variable. And then you just take the derivative. And now we're going to deal with functions going from many variables to one variable. And so we need a generalization of this idea of a derivative, and that's what a partial derivative is. And it is simply a derivative with respect to just one of the input variables. So there's actually a picture here. Okay, so this is another way of drawing a function of 2 variables. Instead of using color, you could actually try to make a 3D plot, which is what this is doing. So now the height is the function f. So this f is also a function of 2 variables, the first variable, the second variable, and then the height is showing the function value. And if you want to take a partial derivative with respect to the second variable, w2 is what it's called in this case, you can think of it as fixing the other variables. In this case, there's only one other variable, w1. So you're just fixing w1 at some value, say 1. And now you're slicing the function. And so now it, again, only looks like a function of one variable because you've thrown away all the other stuff. You're just slicing the function at w1 equals 1. And now along that slice, you have a curve. And you can just think of your regular derivative again, because the curve is just a one variable function. You take the derivative, and that's called a partial derivative because it's only thinking about what happens if I change w2, what happens if I change my second input. It is ignoring all the variation if I change w1. So the general idea with the derivative is I change x a little bit, what happens to f? And the partial derivative is I just change one of my variables a little bit, what happens to f? This is posted, by the way, or at least it should be. Let me know if it's not. So let me see if I can get back to where I was trying to be. Ugh. Ah. Okay, so that was the picture version. Mathematically, say you have this strange function here, f of x, y, z. again, these are functions from multiple inputs to one output. If I want to compute the partial derivative with respect to x, then I just do the derivative to each term just like I do with the regular derivative. And so the derivative of x squared is 2x. The derivative of y squared is 0 because I'm just treating all other variables as the same. I've taken that slice. And so just taking the partial derivative with respect to x, as far as I'm concerned for this temporary moment, y and z are just constants, and the derivative of a constant is 0. So I get 0 here. Derivative of e to the x is e to the x. Just apply the usual rules of derivatives. This is x times some constant yz, so I'm left with yz. So this is much harder to visualize than the regular derivative. The regular derivative is basically the slope. But this is now the slope if I'm only changing one of my inputs. And so if I scroll back, I'll scroll back up for a minute. If you want to think of it in terms of this color plot, you want to find the partial derivative with respect to x. First, you have to specify which y you're doing this at. So for example, y equals 1. Now I have this horizontal slice right here. And now along that horizontal slice y equals 1, it is sort of a thing going up and down. And I can ask myself, what's the rate of change if I'm only changing x? Questions? Okay. Where were we? Okay. Yeah, I think this will be a good time to say something. So if you think about regular derivatives, like, for example, even this function right here, if I take the derivative of this function like I did in my regular calculus class, so let me call this f of x. And let me put on a coordinate system. So if I wanted to plot, sorry, just give me a minute. Just going back to regular old derivatives for a minute. If I said, what is the derivative of this function? Well, I could try to plot that over here for you. So here, it's sloping downwards, so I'm going to have some negative stuff. I don't know. In this part over here, the slope is 0, so the derivative is going to be 0. And then over here, it's sloping upward, and so I'm going to have some positive stuff. So the most important thing I want to say here is that the derivative of this function is also a function. So it doesn't really make sense for me to say, what's the derivative of this, and expect you to tell me a number. That would only make sense if I said, what is the derivative of f at x equals 1? And then you can look it up here and say, oh, it's that. Or at x equals 2, oh, it's that. So to take the derivative of some function is really, you're transforming a function into another function. Unfortunately, we use the word derivative to also mean when we've evaluated this function at some point. So here we'll say, oh, we ask what about at x equals 2, and we'll say, oh, the derivative is 3. That is hugely annoying from an understanding what's going on point of view, because we've used the same word to mean so many different things. So we're going to have to be extremely careful about that in the next couple of days. That, well, the derivative is a thing you do. It's like a verb, really. So I'll call that an operator. It's like an operation, something you do to take the derivative. That is to transform from this function to that function. We also use the word derivative to refer to this new function after you do that action. And we also use the word derivative to refer to the value of it at some particular point. So we'll have to be very careful about that. And why am I saying all this is because it's all the same with partial derivative. All that problems with the wording applies here too. And so taking the partial derivative with respect to x, say, is an operation. It's something you do. But the result is a function. Like this. But it is a function of all the original variables. And that's where a lot of people go wrong. So if I have a function f of x, y, z, and I take partial f, partial x, like I did on the screen, since the original f was a function of 3 variables, my partial derivative is also a function of 3 variables. And you can see that right here. It still depends on x, y, and z. So don't make the mistake of thinking, oh, just because there's an x here, the result is only a function of x. That's a common mistake. Even though I'm only taking the slope, I'm only asking about the rate of change when I change x, I still need to know what x, y, and z are, because I need to know what y and z are so I know what slice to take. We talked about, well, where am I slicing the thing, right? That's the y and z, and then I need to know where x is to know where along that curve I'm taking the derivative, just like here. I need to know, if I want to get a number out, I need to know what x is. Questions about that? Yes, Tom.
I'm assuming you still have to pump in 3 values for x, y, and z.
Exactly. That's exactly what I mean when I say df dx is itself a function of x, y, z. I mean you have to put in 3 values x, y, and z if you want to get a number out. Okay. So yeah, fine. Let's now get to where we've been trying to go all the time, which is gradients. So if you completely understand partial derivatives, which is the hardest part of all this, then understanding gradients is not too hard, because a gradient is really just a container storing partial derivatives. And in particular, it stores all the partial derivatives. So if you have a function of 3 variables, x, y, z, then you have 3 partial derivatives, d by dx, d by dy, and d by dz, and you just put those things in a box. I mean, we call it a vector, but it's just a container, right? And there it is. That's the definition of a gradient. And if you have 4 variables, there's going to be 4 things in the vector, and so on and so forth. So there's going to be some properties of the gradient that we'll have to talk about that are not so obvious. But as far as what it is, it's just a storage container for all the partial derivatives. Which means that this thing is now a function mapping from 3 inputs to 3 outputs. And that's why we talked about that earlier, about 15 minutes ago. We talked about this idea of functions that take multiple inputs and multiple outputs. The gradient function is such a function because in fact, to get df dx to be a number, I need to plug in x, y, and z, just like what Tom was saying. And to get this second thing, df dy, I need to plug in x, y, and z. To get df dz, I need to plug in x, y, and z. So I've plugged in 3 numbers, 3 inputs, but I'm getting those 3 outputs. And again, all that problem with the terminology applies here. But here I'm talking about the gradient function. So the gradient function takes 3 numbers in, gives you 3 numbers out. Questions about that? Okay, let me just, at the risk of being annoying, just repeat myself about the terminology thing. So the gradient operator, the verb, the action to take a gradient, is you take a function f that has multiple inputs, say x, y, z, and you transform it to this new function, gradient of f. You took the gradient, and the new function actually has 3 inputs and 3 outputs. Then the gradient function, which unfortunately we use the same word for, is the result. which is a function mapping from 3 numbers to 3 numbers. And then when you plug in 3 numbers and get out 3 numbers, you will also call that thing the gradient, unfortunately. So when you evaluate it at x equals 0, y equals 1, z equals 2, you might get some gradient like, I don't know, some 3 numbers, and you will call that thing the gradient as well. But it is the gradient function evaluated at a particular point. Questions? Yes, Brendan?
Yeah. In terms of interpreting like a result like that, would we say then that that is sort of the slope for each variable at that point?
Yes. How do we interpret this? So we'll get to that more in a minute. But sure, the one interpretation is just this. So you plugged in, I don't know, some x, y, z, say 1, 2, 3 to get that. So yes, one interpretation is when you're at this point 1, 2, 3, and you change x a little bit, then f is going to change by 2.7 times delta x. And if you change y a little bit, nothing's going to happen to f. And if you increase z a little bit, f will go down by about that same amount. So one interpretation is just interpreting the partial derivatives separately, but we're going to have some other interpretations in a minute. Okay, this next thing is just saying you might not only have 3 variables, you might have d variables, so then you're storing d partial derivatives. Yeah, but this is, let me change something actually, because I'm causing the same problem that I'm complaining about here. Bear with me. So since I just added this x, y, z everywhere to really say, I keep saying this whole gradient is a function of x, y, z, so each individual number in here is also a function of x, y, z, and I should just do the same thing down here as well. I'm just realizing how bad, okay, sorry. I want to make one other change. Okay, this would make me much, much happier. So the usual notation for derivatives people write is like df of x or of 5 or whatever. That's actually a bit messed up because it kind of looks like you're evaluating f. It kind of looks like you're evaluating f of 5 and then taking the derivative, which makes no sense. You're not first evaluating f of 5, which is a number, and you don't take the derivative of a number. So let me write it like I wrote it up there. That's actually what's really going on is the d by dx thing is turning the function f into another function, and then you're evaluating that new function at x, y, z. Okay, so df dx is a new function, and I'm evaluating that new function at x, y, z. Let's do that. Okay. This section is just the stuff I keep saying about the different meanings of the word, so you can read that over later. Let's talk about the intuition of what a gradient really is. So going back to Brendan's question and Annie's question from earlier, what about the direction of this thing? So yes, the gradient is just a box storing a bunch of numbers, but it's also a vector, and there are things we do with vectors like talk about their magnitude and talk about their direction. So let's talk about those things. And this is where we're kind of thinking about the gradient in 2 different ways. One is it's just a storage unit for those partial derivatives, but actually, amazingly, when we think of it as a vector, it has some other properties which are super useful. So the magnitude of the vector tells us in general how fast things are changing. And the direction of the vector, which I've written like this, if that doesn't make sense, you can just ignore that, tells us the direction of fastest change. And so this, some of you may have seen before if you studied this before, and for some of you it will be new. So let me draw another picture. Okay, this we saw before, sine xy. We can take the gradient, in this case by hand. we just take the partial derivative with respect to x, we get y cosine xy. Take the partial derivative with respect to y, we get x cosine xy. Stick those in a container, call it the gradient. And we can actually, so this gradient is a function from two numbers to two numbers. And we talked about how we can plot such things. So here is the gradient. The gradient is a function from two numbers to two numbers, so we can make this type of plot. And we just talked about this type of plot earlier. It's a bit hard to interpret right now, but let me overlay it on top of the other plot. Okay, this I really want to sink our teeth into. There's a lot of stuff going on in this plot. First of all, this plot is showing both the function f in color, sine x and y, and the gradient, grad f, as arrows. So it is showing two functions on the same plot. One is a function from two inputs to one output. That's sine xy. One is a function from two inputs to two outputs. That's gradient of sine x and y. And then I'm sticking them all on top of each other because they both live in the same space, the xy space. And now check this out. This is kind of cool because look at where the arrows are really small. That's where the gradient is 0. That's exactly where nothing is changing in the function. Like right along here, if I move this way, I'm just staying in the yellow territory. So f is the same color of yellow. That means nothing is changing. And indeed, the gradient is 0 there. And same down here in this dark blue area. So this dark blue area is a valley. This yellow area is a hill. But either way, locally, when I'm at the top of that hill or the bottom of that valley, if I move a tiny bit in any direction, nothing is changing. And you see the arrows go away. And how about these arrows over here? Well, these arrows are big. These arrows are even bigger, saying the function can change a lot if I move a little bit, or the color can change a lot if I move a little bit. And furthermore, the direction of the arrow, you can see, is actually pointing straight up the hill, which is not a coincidence. It's a provable property of the gradient, that it points in the direction that, well, if I could go in any direction a little step, this direction will make f increase the most. That is a property of the gradient. Later in this Jupyter notebook, I have kind of a proof sketch of that that's optional. You can read it over if you're interested. But if you don't care, then you can just take it as a property of the gradient. And so actually the direction is interesting to us. And so it is interesting to think of the gradient. And now when I say the gradient, I mean the number version of it. We've already evaluated the gradient function at a point, got two numbers, drawn it as an arrow. That's what I'm talking about. It's useful to think of it as a vector in the way that we talk about vectors and not just as a bunch of partial derivatives. Questions? Jerome.
So if you take an arrow that's pointing like down towards the origin, does that mean that the gradient numbers are both negative?
Yes. So this arrow over here that's pointing towards the origin, that is right. So the arrow is pointing down and left, which means the partial derivatives are both negative, correct? And furthermore, if you go in that direction, you're going up the hill. Sam?
Is there a reason we use both, like, overlaid on top of each other, or is one sufficient to sort of explain?
Well, the reason I'm overlaying them on top of each other is because if you just look at this, you don't really see as elegantly why the gradient is big or small at certain places. But if you look at this, you can connect the two functions and just say, oh, it makes sense that the gradient is 0 around here because if I move a little bit around there, the function doesn't change. So, I mean, it's just a nice visualization to build intuition about what the gradient means. But that's it. Other questions? So by the way, where is this going? What does this have to do with data science? Well, where this is going is that the function f, the colorful thing you're looking at, is going to be our loss function, our error metric, our squared error in linear regression. And these coordinates are going to be things like beta 1 and beta 2. And we're going to be trying to wander around and finding low error points. And the gradient is going to help us get there. So that's why we care about all of this at a very high level. Any other questions about this picture, though? There's really a lot going on in the picture. Tom?
Like, I'm just curious, like, I guess the arrows don't always want to point towards the color, correct? Because you're ending up with like a scenario around like, I don't know, like y is equal to 2.5 and x is equal to 2, where there's like, you can't really see it on the projector, but you can, there's like an arrow there, but it doesn't want to change at all.
There's a small arrow there.
But it's not really pointing towards any color. It's just, it doesn't want to change at all.
Well, if it's truly a zero vector, then it doesn't have a direction anymore. But as long as it's non-zero, you can say what its direction is. That tiny arrow there that's too small to see on the projector is pointing up and right. So the fact that it's pointing up and right means if I move up and right, that's the direction I can go in to make the function get bigger. The fact that it's small means even if I move in that direction, the function's only going to get a little bit bigger. Whereas over there at the place with the big arrow, if I took the same size of step, the function would get a lot bigger. Honey.
Can you go over again what you said about uphill? The direction in which the arrow is pointing is the direction where you're going up?
Correct. So the color here represents the value of f, and you could think about it, it helps with our intuition that the bigger color is like uphill and the lower one is like downhill. And so in this case, yellow is like hills and blue is like valleys. And at each point, the direction of the arrow tells you, if I could only make one little step, that's the direction that would make me go uphill the most for my little step. And then the magnitude of the arrow tells me how much elevation I would gain for that little step. Now we could have this in 5 dimensions or 10 dimensions. We just can't visualize it, so I'm showing it to you all in 2 dimensions. But all this applies to any number of inputs and outputs. Victor?
Yeah. Each arrow is a gradient evaluated in a point, in a specific point.
Yes. Each arrow is the gradient function evaluated at a specific point x, y. 2 numbers come out because the gradient function maps from 2 numbers to 2 numbers, and then the 2 numbers that come out are being used to draw the arrow. Because to draw an arrow, you need 2 numbers, an x component and a y component. And yeah, I mean, I just didn't, there's actually an arrow everywhere. I just didn't want to draw infinitely many arrows because we wouldn't be able to see anything. So the spacing between arrows is completely artificial. I just picked that for visualization purposes. But there exists an arrow at every point because you can evaluate the gradient at any point. Vignesh?
Can we also say that there are multiple local minima and maxima and there's not one for the entire thing?
Yeah, you can say that, but let's leave that for now. Yes, there's maybe a bunch of places where this function is minimized. Yeah. Perhaps all along this curve and this curve or something. Rock.
There's a notation of the magnitude, like double bars.
Yes.
How do we calculate the magnitude?
Oh, right. Scrolling up. The question was about this notation of the double bars, which is the magnitude. That's like the sum of the squares of each component and then square rooted. So it's like the Euclidean length of the vector. Okay. Scrolling back down. Okay, so this is this little proof sketch I talked about. You can read it later if you're interested. Okay, we were supposed to do this, but let's do our break first, and then we'll do those. So let's resume. The symbol for the gradient is this upside down triangle thing. So the symbol for derivative is d over dx. The symbol for partial derivative is curly d over curly dx. And the symbol for gradient is the upside down triangle. The other thing that just came up in discussion with Serg over the break that is maybe helpful to think about, what does this mean? Gradient of f evaluated as 1, 2, 3. At 1, 2, 3, you could think about it as go to the point 1, 2, 3 in your space, and then to get the partial derivative with respect to x, that first component, just move x a little bit. So move to 1.00000123 and see what happens to f. And then that's going to give you this. And then go back to this point and just move a little bit in the y direction and see what happens to f. And that gives you your second component. And then go back to this point and move a little bit in the z direction. It's just, you're actually moving an infinitely small amount. But conceptually, you could think about it as just a tiny amount, if that helps. OK, we have some true or false questions. So take a minute to read them over, and then we'll vote. OK, initial vote individually. Number 1, the gradient of a one-variable function is the same thing as the derivative of the function. Number 2, if we multiply a function by a constant, its gradient gets multiplied by that constant. In symbols, the gradient of AF is A times the gradient of F. Number 3, if one element of a gradient is 0, then all elements must be 0. Number 4, if the magnitude of the gradient at x is negative, the function is decreasing at x. OK, discuss.
Just by looking at it, but I'm not sure. I don't know.
OK, let's do the group vote. So number 1, the gradient of a one-variable function is the same thing as the derivative of the function. So I would say that's true. I mean, if you just think about the gradient, say, of a 3-variable function gives you something, gives you the 3 partial derivatives, 2-variable gives you the 2 partial derivatives, 1-variable basically just gives you the 1 partial derivative, which is just the regular derivative in that case. So sure, why not? Number 2, if we multiply a function by a constant, its gradient gets multiplied by that constant. In symbols, the gradient of AF equals A times the gradient of F. OK, that is true. And it's true for derivatives, and if it's true for derivatives, it's probably true for gradients. When you multiply a vector by a constant a, you multiply each element of the vector by that constant. And since that property is true for partial derivatives, then it's going to be true for gradients. So yes. Number 3. If one element of a gradient is 0, then all the elements must be 0. Okay, that is false. There's just no reason why that would need to be the case. The gradient can be whatever. And number 4, if the magnitude of the gradient at x is negative, the function is decreasing at x. Okay, so I wrote, the question there doesn't really make sense, which was kind of the point of the question to bring up a misconception of terminology. So what does it really mean for the function to be decreasing at x? Well, back to our one variable world, we learned that here the function is decreasing because going down, and here the function is increasing because going up, and here it's flat. But when we have a function of multiple variables, that doesn't really make sense unless we specify which direction we're going. So at some point x, I don't know, is the function increasing or decreasing? Well, it might be increasing if I go that way and decreasing if I go that way. So if the magnitude of the gradient is negative, then that means that the, oh, this is a doubly insane question. The magnitude of the gradient can never be negative because it's a magnitude, and so it's going to be 0 or positive. Okay, that was a bit of a overkill in terms of not making sense question. Maybe I should have said if all the elements of the gradient at x are negative. Yeah. Okay, next. So, loss functions. I'm trying something a bit different this time around. I'm going to talk about loss functions today and then optimization on Thursday, because I noticed in past years there were some things that would get confused together. So we'll see how this works. So, loss functions. Loss function means the thing that you are trying to minimize when you're doing a machine learning thing. So, for example, linear regression. I'll just keep going back to it because it's the most standard example, I guess. Well, you called them betas, I'm assuming. Did you call them betas? Yeah, so we'll call them W's. That's what we use in machine learning. W for weights. Linear regression, the prediction is a weighted sum of the features, so we call them weights. But same thing as the betas that you're used to. And so hopefully this looks familiar. W transpose x, that's the dot product of your coefficient vector with your feature vector. That gives you your prediction. You subtract the true known target value yi, you square it, and you add them all up, and that gives you your squared error. And now you want to find the best regression coefficients, and so you want to minimize that squared error with respect to your coefficients, and so that's what I've written on the board. So before I go on, any questions about connecting what you're seeing there to what you saw in the Regression 1 course? Okay, so this thing is called not the min part. Everything other than the min part is called the loss function. So that loss function is a function of w, and you're trying to minimize it with respect to w. So that's just what the word loss function means. It's a measure of how bad your model is fitting, or just in general something you want to minimize. So this year I'm going to talk about the implications of changing the loss function before we talk about how we actually go about minimizing it. So on Thursday, we'll talk about one way of how we actually go about finding the minimizer, finding the best W. But for today, we won't talk about that yet, and we'll just talk about, well, what might happen if I use a different loss function? What role does the loss function play in my machine learning situation? So here's an example of a different loss function. Did you talk about that one in Regression 1? No one wants to answer. Well, I guess you probably didn't then. So this is just saying that instead of adding up the squared errors, I'm going to add up the absolute value of errors. So the prediction minus the real thing, you know, the whatever it's called, the residual. Instead of squaring those and adding them up, I'm just going to take the absolute value and add them up. That's a perfectly reasonable thing. I mean, as long as the errors are small, it kind of makes sense to minimize such a thing, right? So that doesn't look crazy. And so what is the implications of switching your loss function? Well, first, I have programmed up the squared loss and the absolute value loss. This is just some matrix multiplication way of doing it, but you could do np.sum, whatever, that would work too. Okay, now I'll generate some. Okay, so here's what I did. I generated a data set in 1D, so just one feature. One feature, so you're really just fitting a line here now, not a hyperplane. We're just fitting a line, and I'm actually using scikit-learn's linear regression. So this is not garbage because my code is garbage. I'm using scikit-learn's linear regression, but it looks pretty bad in the sense that there's kind of an obvious trend line with the points, and then there's two outliers, and the whole fit gets messed up. Did you look at this kind of picture in regression 1? Okay. Mix of yes and no, that's fine. So let's talk about this further. So this is a real thing, right? This is a weakness of using the squared error. What's happening conceptually, oh, there's an outlier down here. So what's happening conceptually is that when you're adding up the squared errors, remember that when you square a number, it can get a lot bigger, like 100 squared is 10,000. And so if you just fit the regular line here that's going through most of the points, the residual or the error for this outlier at the bottom right would be even bigger. So the loss function is saying that's really bad. I can't tolerate that big number squared because that's a huge number. And so I'm going to pull the entire line down, get bajillions of little errors that aren't a big deal because they're small numbers and I'm squaring them, and then that's not a big deal. Just to avoid that one number being a really big number squared, because that's horrible. Because that's what the loss function does. The role of the loss function is to tell you which line do I like better. This is just a line, but in general, which fit model do I like better? Do I like this one or this one or this one? Well, the loss function gives you a score for each one, and it tells you to pick the one with the lowest error. And so the loss function is a means of comparing different candidate fits. And the squared error is saying this orange fit is actually preferable to the one that we might like better if we think that this is an outlier and we don't care that much about it and we just want to fit most of the points. Okay, so here's what I'm going to do next. I'm going to use this minimize function, which I imported from SciPy at the top. And so I'm going to call this minimize function on LR loss squared, which is my code. I'll show it to you again. There's nothing weird about it. It's just the sum of the squared errors. I think you used a function like minimize maybe in R when you talked about maximum likelihood, or maybe not. But we'll talk more about this minimize function later in the course. But I'm just telling it, hey, SciPy function minimize, make this loss as small as possible. And here's a starting point. We'll talk about all this on Thursday. But that's fine. Give me my W's. And then I'm plotting it again. So this is to show you that the scikit-learn logistic regression is not doing anything magical. It's just minimizing the squared error. I wrote my own code to minimize the squared error. I get the exact same thing because that is all that is going on in that scikit-learn linear regression or in LM and R. It's just minimizing the squared error. So here I minimized the squared error and I got the same thing. And now I'll just change this one thing from squared loss to absolute value loss. The absolute value loss is my Python function that I wrote up there that I showed you. It just takes the absolute value instead of the square. And now I plot it again. And I get this very different result, this so-called robust regression that seems to ignore the outliers. So we could talk for probably an hour about just this because it's actually, there's a lot to it. It takes a long time to build up the intuition of what's going to change when you change the loss function. It's hard to just solve those optimization problems in your head and know what it's going to do. So there's a lot to talk about. But very briefly, what we said is that instead of squaring things, we'll just take the absolute value. And so we're not going to amplify big residuals by squaring them and making them even bigger. And so here it says, you know what? According to the absolute value loss, this is my favorite line. Because why would I bother tilting the line? Sure, that'll make it better for this one point, but it'll make it worse for those 20 other points, and so it seems like a bad deal. So I'm going to stick with this. Whereas the squared loss said, no, this is the best deal. This minimizes the squared error, and if I tilt it, things are just going to get worse because this big residual is going to get even bigger. Gaurav, yeah.
Is it because squared function minimizer is mean and absolute value is median? Is it because...
It is highly related to that, and I think that's the next thing I had. So yes, here it is. You got it. An interpretation of the mean and median. So you've all heard of the mean and median, but I don't know, you may or may not have heard of this interpretation of the mean and median, where the mean, sorry, I should change this to squared so I don't use terms that we haven't seen. Did you know, maybe you did, but did you know that the mean is the quantity that minimizes the squared error or the squared difference between itself and all the numbers you're trying to take the mean of? So let me show you. Yeah, I should have defined these terms, but L1 is referring to absolute value and L2 is referring to squared error. Sorry about that. Okay, so here's some numbers I just made up. You can download the code, you know, put in any numbers. I'm not making this stuff up. It'll work with different numbers. And I just use NumPy to take the mean and the median. And it just so happens the mean is 23 and the median is 4. And now here's what I'm going to do. I'm going to define a Python function, lambda of x. So it takes in some argument x. And now it takes the difference between x and all my numbers. So x minus 1, x minus 7, x minus 4, x minus negative 3, x minus 3.4. Squares all those errors or differences, and then adds it up. So it's almost like a zero-dimensional linear regression. It's just, I'm giving it one number, and I'm saying, give me the sum of squared errors between that one number and all my values. And then I'm again using this minimize function that I have only briefly introduced and we'll talk more about later. But this is a SciPy function that just minimizes things. And I'm going to say, hey, give me the minimum of that function with respect to x. Find me the x that makes those sum of squared differences as small as possible. And I get numerically 23.2. Next week on Tuesday, we'll talk more about why that's not exactly 23.2, but close enough. I get the mean. And now all I'm going to do here is change that squared to an absolute value. So I'm going to say, here's a different Python function that just gives me the sum of the absolute values of the differences between my input number and all those numbers. And I'm going to use this minimize that minimizes things. And I get more or less the median. So another interpretation of the mean and the median is that if you have a bunch of numbers, the mean is the thing that minimizes the squared differences to all those numbers, and the median is the thing that minimizes the absolute value differences. And going back to Gaurav's question, yes, it is very much related to what we just saw. You've probably talked about in some course or another by now that the median is a more robust statistic because if you have outliers, the mean gets all messed up, but the median doesn't really care. And there's this relationship between mean and squared and median and absolute value, and that's exactly what we're seeing here. And in regression 2, you are going to talk a lot more about this regression with medians and quantiles and all kinds of things. So this connection will be furthered in that course. Yes, Ryan.
So based on the graph here that you're trying to like get the real line,
Yeah.
it seems like you're saying then that those outliers are like invalid data points that should be, if we remove them, we could go back to using the...
Yes, true. So Ryan is saying, well, why don't you just remove the outlier? So this gets into a whole big discussion, which we don't have time for right now, which is, are those outliers junk that should be thrown away, or are they real results that I want to keep? But even if they're real results, how much do I want to let them influence my model? And long story short, you want your loss function to kind of reflect what you care about. And so there's a little bit of a human making a decision here, in that I can't just say, always use this median regression.
So the loss function is kind of giving you a way to kind of say that these are not important, these
You mean can...
actually removing the point, you just use a different loss function to sort of be able to tweak it then.
Okay, there are ways to say certain training examples are less important, but this absolute value thing, in a way, just takes care of that for us, and we don't need to bother saying which ones are the outliers, because it just does the right thing if this is the right thing for what you're doing. Okay, 5 more minutes. So we talked about that. Back to the big picture, right? So we can think of a lot of machine learning as sort of zooming out all the way out to the big picture of these 3 choices we're going to make. Choosing your model, choosing your loss function, and choosing your optimization algorithm. And one of the things I'm hoping by the end of this course is that we start thinking together in this way when we're doing neural networks and all the stuff we're doing later in the course. It's often useful to come back to this 3-part view of what we're doing. So what do I mean by choosing the model? The model chooses the space of possible functions. So if you say you're doing linear regression, then you've nailed that down. Anything you do from there, you will only be able to learn linear functions. And all the mappings you learn from x to y are going to be linear because you just said, I'm doing linear regression. And whatever loss function you do, squared, absolute value, some other weird thing, it's going to look like a line in 1D or a hyperplane in more dimensions. But you've fixed that. Then the second step is, okay, I've picked my model. I'm only looking for linear relationships or maybe nonlinear, just depending on what you chose. Now the loss function says, okay, I've committed to fitting linear functions. Which ones are better than others, given my data set? That's where the loss function comes in. It's a measure of how bad a particular line is. And once you have that measure, you go to step 3, which is let me minimize that loss function. And that's going to be my training, right? My dot fit is going to be that optimization step. And indeed, as you'll see in the lab for this week, that's what's actually happening in scikit-learn. So when you do logistic regression, you're basically picking, well, you're picking 1 and 2. Both of those choices are kind of implied when you pick logistic regression. And then when you do dot fit, it's minimizing that loss function, and that's kind of step 3. And there's some arguments in the scikit-learn logistic regression that allows you to specify which optimization algorithm you want. And so you can actually tweak the way that number 3 is done. So you will be seeing plenty of that in the lab this week. That looks wrong. Oh well. Sorry. There. Okay. Right. So we just have 2 minutes left. So maybe we'll pick up more on this next time. But I just want to briefly show you, because I think you talked about logistic regression and support vector machines in supervised 1. So they're actually the same model, they just have different loss functions. So they're both linear classifiers. Choice number 1 is the same for logistic regression SVMs, but choice number 2 is different. They have different loss functions, and that's why they behave differently, just like the 2 regressions that we just saw. So we don't really have time to go into it in detail, but I made some plots that show the loss function. So this is a 2-dimensional situation where we just have 2 parameters, W1, W2. They're the Yeah, because just a two-dimensional data set that I synthesized. And this is the loss function, so the star is the minimum. This is what ends up getting chosen. But logistic regression looks like this, and SVM just looks like that. It just looks a little bit different. Just like a parabola squared looks a little bit different than absolute value, but that ends up changing everything. And there's some more plots here, so I have some 1D slices of those plots. And yeah, so earlier we talked about squared error versus absolute error, and that top one has something to do with logistic regression, and this bottom one has something to do with support vector machines. We're not going to get to the end of the bottom of this in 1 minute, but basically that's all it is. It's just some slight changes in the shape of the loss, which is saying how unhappy am I with a particular classification boundary, and that completely gives rise to those very different properties of the two models. So that's it for today. I will see some of you in lab today and some of you in lab tomorrow.